Proof from Oslas theorem. So recall Pythagorean parametrization lemma. You can see the lemma says if x, y, z is a Pythagorean triple, i.e., so let's call this, well, x squared plus y squared equals z squared, and this is a triplet of integers. Is the notation okay? Everybody understands what this means? X, y, z is that little e is an element of z cubed. So that means it's an integer and an integer and an integer. It's just a triplet of integers. Mathematicians love shorthand because we are very lazy or in a rush or something. So instead of saying if you have a triplet of integers, you say x, y, z is in z cubed. If that's a Pythagorean triple, in other words, it's a triplet of integers, so that x squared plus y squared is z squared, and primitive, which at first just means, what does it mean to be primitive?
Which doesn't have any common factors.
Doesn't have any common factors. Wait, where are you? Okay, seek. Shake, and Debendra. Shake and Debendra. Right, has no common factors. No common factors. So the 6, 8, 10 Pythagorean triple, Pythagorean triangle is not primitive, but the 3, 4, 5 is. Then there exist integers Rs, coprime, such that we can completely parametrize x, y, and z in terms of R and S. So z is easy, it's the sum of the squares. Now, I'm going to put a 2 somewhere, and they're coprime. We're going to see in a second that only one of them, x or y, one of them has to be even. And by symmetry, I don't know which one. So let's say y is the even one. So assume y is even. Then this will be 2rs, and this will be r squared minus s squared. That's the lemma we're trying to prove, and I tried to argue for you last time that this lemma is extremely old. It's like at least 4,000 years old, because the ancient Babylonians understood it and used it to produce massive Pythagorean triples. Yes? Did we do this last time? We're a little confused? Yeah? You guys remember? Yes, thank you. Good. That's what I need. I need to hear that you're with me. So, right, the exercise was the converse, that if you take any numbers, any real numbers, any complex numbers, R and S, and you make x equal to r squared minus s squared, y equal to 2rs, z equal to r squared plus s squared, then this equation, the Pythagorean equation, will be satisfied by that x, y, and z. So that's always true. The question is, can we go backwards? And the theorem says, yes, we can. So before we, I can tell you the proof. There's a variety of ways to prove this, but the whole point of a course like this is for you to learn how to discover proofs on your own. So before we give a proof, let's try to discover a proof. Discover. This is the discovery phase. How do you solve a problem like this? I mean, really, the discovery phase isn't you're given a lemma, figure out how to prove it. It's discover the lemma. What's the statement? How could you parametrize these things? So let's say we're trying to parametrize a Pythagorean triple. So let's say we have a triple x, y, z with x squared plus y squared equals z squared. 7, 12, 13. Is that right? Yes. 12 squared is 144. 5, 12, 13. 5 squared is 25. 25 plus 144 is 169. Okay? how would you go about trying to find such an R and S? Or how could you try to make sense of this? Is there anything about this shape that suggests something that you should get started with? Want to take 5 minutes and think about it on your own? See if you can come up with some kind of argument for what to do? In groups, like talk to your neighbor and throw out some ideas. Let's take 5. Take 5 minutes, talk to your neighbor. Go ahead.
Yeah, we're trying to just mess around. How do we get started? We're trying to figure out, like, what do you do with this equation? Let's mess around with this equation. Not yet. Okay. Well, can you factor in some of the equations? Over the real, so over the complex. The real sum of variances. Let the new. Try something out. You'll get a feel for what's going on. Any ideas?
Okay, it's a polynomial. I can probably square things.
Okay, right? One idea is to square things. Yep. That'll give us a bunch of algebra and we'll mess around with it. Other ideas? Before we go trying that? Tell me your name again? Karen and Andrew, you were saying something? That's okay, even if it's pie in the sky idea is okay too. Yeah? Syria.
We're try substituting the values, so set like x squared equal to r squared minus s squared.
Okay, so if we set x equal to r squared minus s squared, and we set y equal to 2rs, and we set z equal to r squared plus s squared, we will get, that's what the exercise is. You do the algebra, and this equation will be satisfied. The question is, like that huge, I give you 1,023 and 2,048 and 4,092, whatever. I just made up 3 numbers. How would you figure out what R and S are? You go looking at random. Prime factorization of? Why? Why? Why do you say why?
It's the one you can most methodically find RNS one. I feel like
Good point. I guess since I told you what the answer, maybe I made a pedagogical mistake in telling you what the answer will be. Then you start smelling like, well, if I just factor y and I try the factors of y, eventually one of them has to satisfy this, right? Yeah, maybe before we even get into, there's a little bit to discuss about primitivity, but let's we're in the discovery phase. We don't know the right order to do things, and then we'll give a proper proof. So I gave a hint to the guys in the corner, which was, well, I mean, it's very similar to Karen's suggestion to think about factorization, because, well, I don't know how to factorize y squared, but y squared's over here with x on one side and z on the other side. But here's one very kind of striking thing that will jump out, at least at me and maybe at you after a little bit of experience. So if I bring the x squared to the other side, now I have y squared equals z squared minus x squared. Why would I do that? Exactly. X squared plus y squared doesn't factor over the reals, but z squared minus x squared does. So this factors as, right, z plus x times z minus x. And now something really weird has happened. You have an integer and another integer, and their product is a square. What's funny about a square? When we think about prime factors, for example. I have two integers whose product is a square. What can I say about the prime factors arising?
They're the same.
Or they should be divisible by 2 equally distributed.
Right, so let's think about this. So give me two integers, give me a square. 4 is a little too simple. 25 also a little too simple.
625.
7 minus 12.
How about 36, just to start? Okay, so let's say y is equal to 6, so y squared is 36. The reason things like 169 is 13 squared, or 25 is 5 squared, I still only have one prime to play with, right? So the question is, how can 36 be the product of two things? Well, there's a lot of ways that 36 is a product of two things, right? What are all the 36 is like, well, it's 1 times 36. It's also 2 times 18. It's also 3 times 12, right? I guess let's just keep going. 4 times 9. It's also 6 times 6. Right? These are all the different ways that 36 is a product of two integers, two whole numbers. Here's the funny thing. Can x plus z and x minus z have a factor in common? Some say yes, some say no. Why yes, why no?
6 plus 3 and 6 minus 3.
Okay, so let's just continue the discovery phase. So here's why we thought about primitivity. So if z plus x and z minus x have a common factor, common divisor, so let's say d divides z plus x and d divides z minus x. Then what?
Is it modular classes?
But they're not related, I don't know.
Is it what?
Does it have anything to do with modular classes?
Like modular arithmetic?
Yeah.
We're going to get to modular arithmetic, but right now I just want to do like high school level. Let's just kind of play with our hands, and then we're going to build up technology. But I want you to understand where that technology came from, why that technology was developed, instead of just throwing modular arithmetic at you. Karen?
Then they're not related anymore? They have a shared factor.
Why?
Oh, never mind. I don't
Well-
really know the answer to that.
So does everyone understand what this means? This means z plus x divided by d is an integer. Like 2 divides 6. So if 2 divides 6 and 2 also divides 12, if z plus x and z minus x have a common factor, can we say anything about z and x themselves?
they aren't co-prime?
Why not?
Because they have common factor.
Well, how do I know that z? I know that I know that z plus x and z minus x are not coprime. What about z itself versus x itself? So what does this really mean? It means that z plus x is equal to d times some other integer. Give me a letter. C, d times c. And z minus x is d times another integer, b. What happens if I add these two equations? I get 2z is equal to d times whatever b minus c is. In other words, d then is a divisor of 2z. That means d divides 2z.
Wouldn't it be b plus c?
If I add these two equations, thank you, b plus c, and if I'm getting ahead of myself, and if I subtract the two equations, so this equation minus this one tells me, so if I subtract this minus this, z plus x minus z minus x,
You get 2x.
2x. Okay, so other than cheek, 2x, and on the other side, this minus this. That's why I said I was getting ahead of myself. D times b minus c. Does everybody see that? Who's with me? Okay. Who's against me? I mean, not with me. Everybody's following? Good. Okay, so what does that mean? That means that d divides 2z and d divides 2x. And d divides 2x. Now, initially, all we assumed is that x, y, and z have no factor in common. So, for example, so if there does not exist a number, let's call it L, dividing x and L dividing y and L dividing z, that's what it means to be primitive, right? Then x, y, z is primitive. I claim there's an even stronger primitivity that's required on primitive Pythagorean triples, which is that there's no integer that divides both any two of them. So what's the distinction between primitive and pairwise primitive? So there's primitive and pairwise primitive. Primitive is that the greatest common divisor, is it okay if I write this? Parentheses xy, that means that's the same thing as GCD of xy is 1. Greatest common divisor of x and y is 1. Everybody understand what I mean by that? There's no prime factor in common with x and y. So pairwise primitive, which means x and y have no common factor, and y and z have no common factor, and x and z have no common factor. So all the GCDs, the GCD of x and z is 1, the GCD of y and z is 1, the GCD of x and y is 1. Are these two the same thing? Is pairwise primitivity the same thing as this triplet xyz is primitive? There's no number, this says if there exists a common divisor, then this thing is primitive. So I want to say, if there does not exist an L greater than 1, if there does not exist an L greater than 1 that divides x and divides y and divides z, then this triplet is primitive. Right? So what do you think? Is primitivity the same thing as pairwise primitivity? Is pairwise primitivity a stronger condition?
Pairwise is stronger, right?
Why?
Because if say z was 1, then x and y could be, then that would make the whole thing primitive.
Yep.
Or if one number is prime, then
Yep.
everything, yeah.
So one more time your name, I'm going to get it. Stephanie. So Stephanie's example is, look at 2, 4, 1. That's a triple. Is that triple primitive? There's no number that's going to divide both x and y and z because there's no number other than one that divides z. So it's automatically primitive. Right? This is primitive. Is primitive. Is it pairwise primitive? The GCD of y and z. 1. Everybody see that? The GCD of x and z. 1. The GCD of x and y. Not 1. Okay? So it's primitive, not pairwise primitive. Not pairwise primitive. How about another example, just where none of the numbers are 1? Does this only happen if one of the numbers is 1? Let me give you another example. 2 times 3 is 6, 2 times 5 is 10, and 3 times 5 is 15. Is this primitive? What divides both 6 and 10 and 15? Well, 2 divides these two, but not this one. 3 divides these two, but not this one. 5 divides these two, but not that one. And nothing else. Okay? So this is a primitive triple. This is primitive. It is primitive, but it's not pairwise primitive for any pair. Every pair has something in common. 6 and 10 have 2 in common. 10 and 15 have 5 in common. 6 and 15 have 3 in common. But the three of them together are a primitive triple. Okay? Does that make sense? So there's a distinction between pairwise primitive and primitive. If you're pairwise primitive, if no 2 of them have any factors in common, then of course the 3 of them don't have a common factor. But the other way is not necessarily the case. So it might be the case that z and x have some common factor, but zx and y don't have any common factors. But in fact, for Pythagorean triples, primitivity, this weaker notion, implies the stronger notion. Let's see if we can prove that. Let's see if we can see why that's true. So, but for Pythagorean triples, primitivity implies this pairwise primitivity. Pairwise primitivity. Why? Let's say x and z are both divisible by 5. Could it be that y isn't divisible by 5 if x and z are? Other than Karen? Who said that? Tell me your name?
Sarah.
Sarah.
I would say no, because in the example you're doing y squared equals 300 is the motion x minus z and then times x plus z.
Yep.
When you because there's like a common factor there, and then that means the other one also has to have that with it.
Beautiful, beautiful. So the reason for this is, let's say 5 divides x and 5 divides z, then y squared is equal to z squared minus x squared. But z squared minus x squared will be a multiple of say it again? 25. Not just 5, but 25. Because this is now a multiple of 25. This is now a multiple of 25. X and z were both multiples of 5. This is a multiple of 25. So this is, so 25 divides z squared minus x squared, which means 5 divides y. So if any 2 of them have any factor in common, then all 3 of them by this equation are forced to have that factor in common. Does that make sense? Exactly what Sarah said. So if two of them have a factor in common, all three of them must. In other words, if the three of them don't have a common factor, no two of them can have a common factor. Let's write that down. Let's write that down. What we've shown, maybe it's worthwhile even to make it a lemma. Lemma. If x, y, z is primitive and Pythagorean triple, then pairwise primitive. And the proof, for the proof we can prove the contrapositive. You guys remember these logic words, contrapositive? What does contrapositive mean? If I have a statement P implies Q, the contrapositive is?
Q and not Q implies.
Not Q implies not P. So not proof contrapositive, so let's state the contrapositive. Not pairwise primitive implies not primitive. Okay? In general, this is not true, but for Pythagorean triples, because they satisfy this extra equation, x squared plus y squared equals z squared, this is true. And the proof is, so, not pairwise primitive, so there exists some L dividing, let's say, x and L divides z. That implies L squared divides z squared minus x squared, but that's y squared, which implies L divides y, which implies not primitive. Does that make sense? Is everybody following? Who's lost? Be honest. Karen, can I ask you to raise your hand? Who's lost? Okay, still nobody. Sometimes that helps. Thank you. Okay, everybody's with me? This makes sense? Am I going too slow? For how many is this too slow? Be honest. Karen, raise your hand. How many is this too slow? Still nobody. Okay, good. All right, so if we have a primitive Pythagorean triple, then actually they're pairwise coprime. Let's go back to the question about, I guess I can put this here. This is the fun of having this. So what we saw before is when we factor x squared, z squared minus x squared, we look at x plus z and z plus x and z minus x. So if these two numbers have a common factor, then if d divides both z plus x and z minus x, then d divides 2z and d divides 2x. But if we had a primitive triple, x, y, and z were coprime as a triple, that means they were pairwise coprime. So z and x have no factors in common. Let's write that again. So if d divides z plus x and d divides z minus x, then d divides, well, I don't know about z, but I certainly know that it divides 2z. And d divides 2x. Does everybody follow that argument? Yeah, because it's right here. If z plus x is a multiple of d, z minus x is a multiple of d, you add the two, 2z is a multiple of d, and you subtract them, 2x is a multiple of d. So d divides 2x, d divides 2z. But z and x have no factors in common, but the greatest common factor of x and z is 1. They have no factors in common. That implies what? We're assuming we have a primitive triple. So d divides 2z and d divides 2x, but x and z have no factors in common. So what's a number that divides twice z and it divides twice x? other way around, that would be if 2z, so maybe it's this notation. 2z is a multiple of d, and 2x is a multiple of d. But x and z are coprime, have no factors in common. So think about prime factorization. So this is 2 times the product of all the primes and their prime powers that divide z. And d is some combination of all of those. And 2 times all the primes multiplying x is what this number is. And d is some combination of those. But these primes and these primes have nothing in common. Tell me your name?
Surya.
Surya.
So they only have 2 in common?
They can have at most 2 in common. Exactly. That means d is 1 or 2. They can have at most 2 in common. Does that make sense? If you just think about the prime factors, so let me move this. If you just think about prime factors, this is equal to 2 times a bunch of primes to their powers, p1 to the e1, pn to the en. And this is 2 times, let's say, q1 to the f1 and qm to the fm. But the p's and q's are all different because x and z are coprime. And d, well, it's also an integer, so it's some product of primes, and it has to be some of the primes that are in here, and it has to be some of the primes that are in here, but these are all different from these. The p's are different from the q's. So the only thing d can be is, well, it could be 1, it could be nothing, don't take any primes, or it can be 2, because there's a 2 in common to both of these. Question?
Is 1 considered a trivial solution for d, or?
Yes. Yes. 1 is the divisor of every number. What I want to rule out now is I want to rule out 2 as being a divisor. Well, let's think about this. So what have we done? What do we say? We had a Pythagorean triple. So our example, let's run with this example. X, Y, Z is 5, 12, 13. Right? So what we said is 12 squared is 13 squared minus 5 squared. But 13 squared minus 5 squared is 13 plus 5 times 13 minus 5. And 13 plus 5 is 18. And 13 minus 5 is 8. Did I get that right? Is anyone checking any of this arithmetic? Let's see. Sorry? 144, yes, 18 times 8, 144. So far, so good? All right. Now, remember what we said. We said y is going to be the even one. So we already know, so we assumed y was even. We assumed y was even. By the way, we didn't talk about the parity. What are the possible parities? By parity, I mean even odd. What are the possible parities of x, y, and z? Possible parities. Parities of solutions. So, let's see. Once we go through the discovery phase and we sort of figure out everything that we want to know, then we'll be able to prove it in a nice, slick, one paragraph thing that you're used to. I'm trying to train you to discover these solutions and then be able to write them up in a nice way. So what are the possible parities? So could we have odd squared plus odd squared equals odd squared? Could they all be odd? X, Y, and Z. Could all 3 of them be odd? They can't all be odd because an odd squared is odd, and an odd squared is odd, and an odd plus odd is odd times odd is odd, odd plus odd. Right? 7 plus 13, 2 odds. 1 plus 1 is 2, right? So, yeah, should we prove this formally that odd plus odd is odd? Might be a good exercise, actually. But here's a test. Okay, you have 2 minutes to give me a formal proof that an odd plus an odd is even. Let's see if you know how to write one down. So here's an exercise, not an exercise for home, an exercise for right now. Let's call it a lemma, which is that odd plus odd is even. I'm still gaining, I'm still trying to understand what you guys know. So if this is too slow, we'll see it immediately. If you have any trouble with this, I'll know not to go too fast. Alex.
Alex, if I was to say, if you let A and B be two odd
Yes.
numbers, then A equals 2 R.
You're giving me the proof. Yes, write it down. Yes.
Oh, sorry.
Yes, that's. So for those that heard what Alex was saying, he's giving the way of doing it. So, i.e., let's do what Alex said. If A and B are odd, A plus B is even. So proof. Now take 1 minute and try to write down a proof on your piece of paper and convince yourself that you've written a complete proof. And then give me a thumbs up when you got it. What does it mean for a number to be even? It's a multiple of 2. So I hope whatever you've done at the end has 2 times an integer, and that's why you know that your number is even. Is that a thumbs up in the back? Thumbs up? Thumbs up? Okay. Some people are still writing. Give them a minute. Good, I like it. Everyone's still going. Okay, show of hands who's done. Couple still working on it. Give you 10 more seconds, and then we'll all join together. Okay, who thinks they have a proof other than Alex, who already told me one, and other than Sheik? Tell me your name. Evan. Kevin. What's your proof?
Suppose we have A, B as elements of C.
Uh-huh.
And A and B are odd.
Okay, so if A and B are odd, then?
By definition, we can express A, B such that A is equal to 2K plus 1, B is equal to 2J plus 1, where K and J are both integers.
Uh-huh.
It follows that A plus B is equal to 2K plus 1 plus 2J plus 1. And once we like simplify it, we actually get something. We get A plus B is equal to 2 times the quantity of K plus J plus 1. And since K, J, and 1 are all integers, and integers enclosed under division, we can express 2K plus J plus 1. K plus J plus 1 that is also an integer, as which we will denote as I just said T.
Okay.
So eventually we get something like 2.
No, that was perfect. That was a perfect proof. Let's read Kevin's proof. If A and B are odd, then what does it mean to be odd? Odd is you're one more than a multiple of 2. You're not yourself a multiple of 2, you're one more than a multiple of 2. So there are integers, so then A is equal to 2K plus 1 and B is equal to 2J plus 1, where J and K are integers, with J and K in the integer. Then what happens when you add A and B? A is 2K plus 1, B is 2J plus 1. This is simple algebra. 2 times K and 2 times J and 2, the 2 you can pull out, you get J plus K plus 1. But J and K and 1 are all integers, so their sum is an integer. So A plus B is twice an integer, So A plus B is E. Great. This is Math 300. Everybody's comfortable with this level of argument. Awesome. So can the solutions be odd plus odd, odd, odd? Will a triple of Pythagorean numbers, will a Pythagorean triple ever be 3 odd numbers? No, because an odd plus an odd squared is odd. Again, you want to prove that lemma? Odd squared is odd? Is that a good exercise? I'll put it on homework. I'll put it on the homework, not now. So exercise, what number is this? 3. Exercise 3, odd squared is odd. Okay? Easy homework problem. So what does that mean? So no Pythagorean triple has all 3 odd. Fine. You can't have odd, odd, odd. Can you have even, even, even?
In theory, yes, but I feel like the answer is no.
You're both right. I didn't specify what I mean. We assume primitivity. So yes, you can have 3, 6, 8, 10 is a Pythagorean triple, but we want the primitive ones. So if they're all even, if all even, then it's not primitive. And we decided we're going to only focus on the primitive ones because you can always pull out all the prime factors. Okay? So we've ruled out 3 odds, we've ruled out 3 evens. How about even, even, odd? So could we have, so here, let's make a table of everything. There's odd, odd, odd. How many combinations are there of things to try? 8. Because there's 2 odd or even for each of the 3 variables, so 2 cubed. So there's odd, odd, odd. There's odd, odd, even, odd, even, odd, odd, even, even, odd, odd, even, odd, even, odd, even, just in time, even. 1, 2, 3, 4, 5, 6, 7, 8. Those are the possibilities. Kevin?
Do we really need to do EO and because it's
Okay, let's get a couple of things. Symmetric. So if this is x, y, and z, if this is our table of parodies for x, y, and z, what Kevin is saying is odd, even, even is the same thing as even, odd, even. Because x and y are, we shouldn't bother considering both of those. We're going to do that in 1 second. We're going to use that symmetry in 1 second. First, let's just rule out a couple of things. Even, 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 we just ruled out because we want primitive solutions. So this is imprimitive. Odd, 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 we ruled out because odd plus odd is not odd. Maybe I should add to this exercise, and even squared is even. So how about odd plus odd is even? Any reason to rule that out? No, right? Makes sense. Odd plus odd could be even. Let's leave that for now. Odd, even, odd, that's exactly the case that we're trying to think about. If x is odd, y is even, and z is odd. So these two we're not going to get rid of yet. Odd, even, even. An odd squared plus an even squared will be odd. So odd, right? The squares don't change the parity. So forget about squares. Just think about odd plus even. Is odd plus even or odd? Odd. So this one's gone. How about even, odd, odd? Kevin? How about even, odd, odd? It's
no. Wait. Yes.
It's symmetric.
It's symmetric. By your symmetry, by Kevin's symmetry, we don't have to consider even, odd, odd. We can just think about odd, even, odd. Because we can flip. Okay, so this is the same thing. So we don't need to consider it as a separate case. Even, odd, even. Even plus odd is?
Because the odd plus even is equal to an odd less than an even.
Yep. Yeah, you could use symmetry, or you could go back to an even plus odd is odd, not even. So either symmetry or just parity. That can't be. How about even plus even being odd? No. Even plus even is even. Okay. So because of the symmetry, let's just cross this case out. We already have it there. This should have been crossed out. So there's really only two possibilities. X and y are odd and z is even. Or the possibility we're thinking about, which is odd, even, or odd. Why can't this happen? I claim this can't happen. Karen.
Didn't we say we wanted Z to be odd, like that in the beginning?
We did say that. That should have been part of the theorem. If xyz is primitive, then z is odd. I claim this case can't happen. Alex, you got an idea?
So if z is even, then z squared is even, and z squared is x squared plus y squared.
Uh-huh.
So if 2 divides z squared, then we would divide x squared plus y squared. Is that on the right track?
But that's in the right direction. Let me give you guys, this is a hard one. Should I give this as an exercise, or should I? This is slightly not, I haven't yet given you the tools for this. I want to see what you've discovered. One more, Steve.
Yeah.
Dan.
We can look at it mod 4, I think.
Okay. So Dan has, yes, we can. Should I, all right, let me tell you that, so we don't have to talk about mod just yet. We'll get to modular arithmetic formally. I still want to do this, in a rough and tumble kind of way. Look at what happens in this case. I want to rule out this case. So this is the case that x is 2, give me a letter, a, 2a plus 1. Y is 2b plus 1. And z is 2c. X and y are odd. Z is even. I claim this can't happen for a Pythagorean triple. Let's look at, so if x is odd and y is odd and z is even, then let's look at x squared plus y squared, x squared plus y squared, well, equals z squared, but let's look at x squared plus y squared. What is x squared plus y squared? Well, what is x squared?
4a squared plus
4.
1 plus
Yes?
4a.
4a squared plus 1 plus 4a. Right? That's x squared. And y squared is?
4b squared plus 4a.
So other than Sheik, does anyone else know how to multiply? Yeah, we all understand this, right? And what about z? So that's supposed to equal to z squared. 4c squared. And here's something much more subtle that's going to happen. Why can't this have a solution in the integers? Yes, because these, look at the numbers that are multiples of 4. So these numbers are multiples of 4. The fancy way of saying this is to look mod 4, but we'll get to modular arithmetic formally. How many have seen modular arithmetic? Okay, not everyone. So we will do it properly and slowly and so on. So these numbers are all divisible by 4, and what's left over here is this number is going to be 2 more than a multiple of 4. This number will be a multiple of 4. Can't have both. Can't be equal. Okay? Let's just say that formally. Let's call this a lemma. If x squared plus y squared equals z squared, then can't have x odd, y odd, and z even. Not because of parity, not because an odd plus an odd does make an even number. So we don't just look mod 2, we have to look mod 4. And the proof is exactly what we said there. proof. Again, I mean, it's exactly what's written here. So I'll just rewrite 4 times a squared plus a plus b squared plus b plus 2 would be equal to 4 times c squared, and this is impossible. Does that make sense? Everybody happy with that analysis so far? Okay, let's go back to our table. We can still see our table. There's our table. So odd, odd, even has just been ruled out. This can't be. So the only possibility is the one that we're working with. That's why we're working with that one. X is odd, y is even, and z is odd. Okay? Good. Back to, where were we? Where were we? So we looked at we had assumed that y was even. Why did we assume y was even? It had to be even. There's no other option. Well, or x could be even and y could be odd, and then we use symmetry to switch them. Right? Does that make sense? So question? No? Okay. So where in the proof are we? In the proof of what? We're still trying to just discover how to find this R and S. So assume y is even, then y is equal to 2 times, let's just call it y1, so we remember. If you start using A's, B's, and C's, then you don't remember where it came from. And y squared is z squared minus x squared, which is z plus x times z minus x. And y squared is 4y1 squared. Question?
Is that when you say y is equal to 2y, is that oh,
so if y is even,
okay,
then y is equal to 2y1.
Okay.
That's meant to be a 1. I would put a prime, but we have a lot of squares, and primes and squares start looking like 12s, or you have to put a million parentheses. So I just put it as a subscript. Is that okay? To call the variable y1? That's not going to confuse anybody? All right. Remember, x and z are both odd. So x plus z must be even. And this must also be even. So let's give these names. What should we call this even number? 2r. Let's call this 2r. And let's call this something. Oh, I'm using r. Okay, 2a. And this is 2b. Does that make sense? So what do we have now? We have that 4y1 squared is equal to 2a times 2b. So y1 squared is equal to ab. And what are the prime factors of, what are the common divisors of a and b? We even almost have everything we need on the board. So a is 2z plus x, and b is 2z minus x. If we have a divisor, a common divisor of both of those, then that common divisor is either 1 or 2. But z and x are both odd. So z plus x is even, and z minus x is even. So we actually know what d is. We know what the common divisor is. 2. And what does that mean? So the common divisor, so GCD, greatest common divisor of x, z plus x, and z minus x, is 2. So the greatest common divisor of a and b is I have an even number and another even number, and the greatest common factor of them is just the number 2, not 4, there's no other primes in common. So if I divide out by that common factor 2, what common factors do I have left?
One.
Nothing. I have nothing left. I have 1 left. Exactly. Everybody see that? So let's look back at our hypothetical solution here. It's right there. 12 squared is 13 squared minus 5 squared. That factor is 13 plus 5 times 13 minus 5. 13 times 5 is 18. 13 minus 5 is 8. Maybe you didn't notice anything about 18 and 8. But 18 is twice 9. And 8 is twice 4. And 9 and 4 are not arbitrary numbers. They are perfect squares. Why must they be perfect squares? Bless you.
The multiple of 2 perfect square is perfect.
Okay, good question. Is the multiple of 2 perfect squares a perfect square? So here's an aside. If I have a perfect square k squared, and I have another perfect square L squared, and I multiply them together, do I get a perfect square? K times L squared. Yes, so the product of 2 perfect squares is a perfect square. What we want is actually the converse. We have 2 numbers with no factors in common, but when you multiply them, you get a square. Remember, it's possible to multiply 2 numbers and get a square with those 2 numbers not being themselves square. 18 is not a square, 8's not a square. They multiply together and they make 12 squared. But when you divide out this factor of 4, what you're left with, if I divide out a factor of 4 from 12 squared, that's writing 6 squared as something. Am I making sense? Alex, you want to say something?
No, so.
So what am I trying to get you to conclude?
Is it A, B under the radicals in the
Yes, that A is itself a square and B is itself a square. Think about the prime factors of the number y1 squared. Whatever y1 is, it's some primes, and now you're squaring it, which means you're doubling the power of each prime that, as it appears. So here there's like, a 7 to the 3rd power and a 5 to the 8th power or whatever. When you square it, you get a 7 to the, 3rd power? 6th power, and a 5 to the 16th power. And that, whatever that prime factorization is, has to appear in either A or B, but it can't appear in both. There's no prime in common between A and B. So all the primes, so y squared, you can think of y1 squared, this number y1 squared, as splitting into some p's to twice a power times some q's to twice powers. And A and B have no, A has only p's and B has only q's. So what have we learned about A? It's a square. And what have we learned about B? It's a square. So A and B are perfect squares. That means that A and B are squares. Again, we're still at the hand-wavy phase. We're getting to know each other. We're getting to know each other and we're getting to know the subject. When we start doing this rigorously and formally, we'll have, we'll do this properly. But I find when you do it properly from the very beginning, it comes out of left field. Why are we doing it like that? So I hope you're appreciating kind of the point we're trying to make. So what does it mean that they're perfect squares? That means that A is a square of a number, let's say R, and B is also a square of a number, let's say S. What would that be in our example up here? How do I show you both? Like that. What would that be in our example here? This was A and this was B. So R is
It's 3.
and
2. S's.
and S is 2. Right? Which is exactly what we found last class but we found it just by guessing, by messing around and guessing. Now you don't have to guess. You just literally look at the number. It's going to be twice the square. Take the square root. And same thing here. So you take z plus x. That's going to be twice a number. You have it. You get a number. That number must be a square. You take its square root. That's r. That's algorithmic now instead of let's try all the factors and hope we get lucky somewhere. Does that make sense? So if a is r squared and b is s squared, well, we know that, so what do we know about right here? Remember, z plus x was 2a and z minus x is 2b. So z plus x plus z minus x will be, this was 2a and this was 2b. So what does this come out to? What does this come out to? 2z. A we said was r squared and b we said was s squared. So we get 2r squared plus 2s squared. So z is r squared plus s squared. And remember what y squared was. Y squared was 2a times 2b. So y squared is 2 where am I? Right. Let's go here. y1 squared. So 4y1 squared is 4ab. From this equation, 4y1 squared is 4ab. A is r squared, b is s squared, 4r squared s squared. Now I can take square roots of both sides. 2y1 is 2rs. And what was 2y1? Y. So y is 2rs. Cool? You guys appreciate this? Let's literally do that Babylonian one. So let's do an example, and then we'll give a formal proof, and then we'll start developing more formally. But I do want to give you the flavor of the kinds of. You should always, whenever you're doing formal things, what I find is that when people start doing these things formally, they follow line by line formally what's going on, but then they lose the essence. You're not getting your fingernails dirty anymore with the actual numbers and what's happening. You're following sort of the formalism of it, and you're getting caught up in that. So it's good to be able to go all the way to the clouds for the purely formal argument, and all the way down to the dirt and deal with numbers and get a feel for things. Okay, that's what I want you guys to be developing. Good. Let's do an example. So example. Let's see if we can work this out on the fly. Example. This is this Babylonian tablet. Line. What line did we work out last time? 7. Row 7. Row 7. We found a diameter of 3541, a width of 2291. That's what we worked out were the two numbers that were there. And d squared minus w squared turned out to be a length of 2700. Okay? Let's work out. So in other words, this was like, this is x. This is what we had been calling x. This is what we had been calling y, because it's the even one. This is what we've been calling z. First of all, are these numbers coprime? Looks hard, right? You have to think about, by the way, how do you check the two numbers are coprime? You compute their prime factors and you look at what's in common? Okay, we're going to get to Euclid's algorithm soon. Computing prime factors in grade school, throughout college, I think I was told you just compute the prime factors. And then I realized we don't know how to factor. You think you know how to factor? If we knew how to factor, we would not be able to buy crayons on Amazon. Nobody would use a credit card if we knew how to factor. In fact, if quantum computers really make it, then we will know how to factor, and then we're going to have serious problems with. We'll have to wait a lot longer to buy our Amazon gift cards online. Has anyone taken cryptography? You have any idea what I'm talking about? Okay, so some of you have taken cryptography. Right, we don't know how to factor. We do not have good factoring algorithms. You give me a 30-digit number and another 30-digit number, I will very quickly, well, the computer will very quickly multiply them together. A computer will not very quickly factor a 60-digit number. Unless it's a quantum computer, which at the moment is still only hypothetical. Bless you. So factoring these numbers is not a good idea. But computing the GCD, the greatest common divisor, there's an extremely efficient algorithm, which is Euclid's algorithm. We'll get to that in a minute. There's kind of a cheat that we can use here. Remember, we're worried about triples primitivity of all three, but we proved that it's enough to check primitivity of 2. If 2 are primitive, then all 3 are primitive. Because if all 3 are primitive, then any 2 is primitive. Every 2 is primitive. How about 2700? What are the prime factors of 2700? Well, it's 27 times 100. So we can just read it off. In this case, we can't factor. I just gave a whole thing about how you can't factor. And we're looking at this 4-digit number we can factor instantly, or at least we can figure out what the prime factors are. So the prime factors of 27, 3 cubed, yep. So there's 3's here. How about 100? 2's and 5's. So we have 3's, 2's, and 5's. Is a 2 going here? There's a 5 going here. So the only thing we have to worry about is 3. You know how to check if 3 goes in a number? Add the digits. So 1 plus 2 plus 9 is multiple of 3, but that extra 2 isn't. Okay? So these two numbers are co-prime, and that's it. We win. We can apply our theory. So what does our theory say? You take y squared. So what we know is that y squared, you want to take a minute and work out R and S? See if you can understand the proof enough that you can very quickly, you might need a calculator to, all you're doing actually is adding and subtracting numbers that are not that big. So maybe you won't need a calculator. But try to work out R and S. Let's take 5 minutes. Try to work out R and S. See if you can do it from what we just did. And cheat, talk to each other, work in groups. Look on your neighbor's page. On a quiz, that's not allowed. This isn't a quiz. It's encouraged. Everybody's off to the races by themselves? Give me a hand if you're done, or give me a hand if you need a hint. So y squared will be that squared, and that'll be 4a.
Oh.
And where did that come from? What was A and what was A? I think it has to be bigger than 5 and 2. And then R squared is 25, yeah, and S squared is at 4, yeah. And you're going to add 25 and 4 and get up to 35, 41. You want two numbers whose squares add up to 3541. Their difference is 2291, and twice their product is 2700. It would be rather non-trivial if we had to just prove this theorem. really getting it. That's awesome. How many have it already? Just a show of hands. 3, 4. Give you another minute. Exactly. Yeah. So we want find R and S so that Z is R squared plus S squared, X is R squared minus S squared, and Y is 2RS. We're trying to find the parametrization. Which R and S did this solution come from? Found it? Okay. Look back over the proof. Just follow the proof, and everywhere we had variables, work out what it is in this case. Got it? Works, right? It's amazing when it works. You have to think. You just follow the proof. It's an algorithm. That's the beauty of it. So go back to how we figured this out. What did A and B come from? Since we're going to run out of time, let's do it together, and I'll give you row 8 as an exercise at home for you to practice again. So how many got it? And what's the answer? Altogether? 54 and 25. So the claim is that 54 and 25, if you take 54 squared plus 25 squared, you'll get that. If you take 54 squared minus 25 squared, you'll get that. And if you take twice 54 times 25, you'll get that, which makes sense because this is twice 27. 27 twice. You know what I mean. How would you figure it out? Again, y squared is z squared minus x squared, which is z plus x times z minus x. What is z plus x? I know what z is, 3541. X is 2241. I add these two. Did anybody do it? Don't make me do it in my head. You gonna make me do it in my head?
5832.
5832. Z minus x, so that's 3541 minus 2291. What is it? 1250. So remember our proof, this number is supposed to be twice a, and this number is supposed to be twice b, but a and b are supposed to be perfect squares. So what is half of this number? Half of 58, 29, half of 32, 16. And what about b? Half of 1250, half of 12 is 6, half of this, that's that. And both of those numbers are supposed to be perfect squares. So you don't have to guess, you just literally hit it with the square root button. So what's the square root of 625? Square root of 625, well, I told you already, 25. And square root, so this is supposed, oh, sorry, that's s. And this is r squared. So r is the square root of 2916, which apparently is 54. So that's what I mean by, Sarah, right? Sarah. So that's what I mean by, when we got to what y squared was, we start looking at the prime factors, we start guessing, we don't know what to do. The beauty of this is no thinking.
I've been working on the 2RS part. That was where I was getting
Right, right. If you start working on the 2RS part, then you have to guess.
Yeah.
And the beauty is, you don't have to guess. Look at z plus x. That'll be twice r squared. Divide by 2, take a square root. That's r, period. Same thing with this. So, right, so there really isn't that much to do. And let's make an exercise. Exercise 4, is it? Exercise 4. Compute R and S for row 8 in the Plimpton tablet. Okay?